Recording.
This meeting is being recorded.
Recording is in progress. This is perfect. So I propose to begin this session about the Corona Borealis, for which Novae outburst, is expected soon, very soon. We don't know exactly when, in fact. And I propose a short introduction before giving the micro to Steve, and about the current status, in fact, of CrB. We have now more than 1,600 spectra in the database. This is a formidable input. I want just to show first a very schematic view of CrB system, which is an interacting semi-detached binary with a white giant M4 subtype, which orbits with a white dwarf, very massive white dwarf. The estimation is more than 1.2 solar mass. Thus, the white giant is distorted by the interaction with the white dwarf, and emits a stream of matter from the Lagrangian point 1. The matter is accreted toward the white dwarf through an accretion disk. The orbital period is small for an symbiotic system, less than 1 day. 1 year, sorry, excuse me. The particularity of CrB is that it is a recurrent symbiotic nova. First, a symbiotic with a donor star, an accreting star, an accretion disk, which produced 2 nova events. First one in 1866, second one in 1946, thus about 20 years between the 2 events. And this is recurrent because it is not different from classical nova. We say recurrent because 2 outbursts was observed at a human time scale. Here is Lie curve of the 1946 event from the Dutch values, showing that before the nova event here in 1946, there has been, this is B magnitude, in fact, there has been an increase of the luminosity, which preceded, in fact, the nova event. Here is, on the right, zoom on the nova in itself, showing the end of the active, the nova event in itself, and peculiar shape of the Lie curve a few months after the Novae event. Now, we are at the beginning of the new century, and AVSO observers in photometry produced a very nice light curve, in fact, of the favorite target since in B and V band since more than 10 years. Of course, from AVSO observers and also AFOEV and other amateur organizations, we have visual observations during all the last century. Thus, like curve, here the B and there the V like curves, we have clearly from 2015 a significant increase of the luminosity for about 8 years, which can be called a very high state in comparison with the oscillation in quiescent state. Both photometric observers and observers with spectroscopy detected at the beginning of 2023, exactly in April, the end of the very high state, and after a very, very low state. In our spectra, even Balmer lines are very, very faint. One can see that we have an increase of the activity of the system during 2024, and especially at the end of 2024, with our spectroscopy, we have detected a new, I would say, not exactly high state, but a flare with a duration of about 15 days. So one can see that the activity of the system is regaining, in fact, at a level which is intermediate between low state and very high state. This flare we have described, this flare in research note with the observers and with the support of Steve. Here, I show the flare. What is important is first, I will give the flux of H-alpha line, showing here the end, in fact, of the very active state, the very low state, the regaining of the activity of the system, and there we are in November 2024. And what we detected with our spectra is here in black the level of the flux of H-beta line, which increase very suddenly at this date. We have an uncertainty of a few days, in fact, but also the reappearance of ionized lines, such as He2 or He1. This is a very nice observation, in fact, because thanks to the involvement of several observers, especially Woody Sims, Robin Lidbetter, Kelschank, and so on, we have a very precise description of this flare. Now, to put this event in perspective of the evolution of the system, I'll build, in fact, a smooth line of the luminosity in B band according to the orbital mass of the system. Due to the shape of the white giant, which is distorted first, and also due to the of the nebula, we have a double wave variation of the luminosity. Here is in blue the smooth line curve of the cycles out of the I state in blue. And here is the line curve of the system during the very high state, 2015 to 2023. One can see the last cycle there. We are now there at the end of orbital cycle 110 according to Linus ephemeris. Thus, we are in fact in peculiar phase. Here, the flares that we detected with spectroscopy in last November, and here the current state of the system, for which we have what we didn't have during the very low state in 2023. We have HA2 and a significant level of Balmer lines with an equivalent width of about 20. Here is a very recent spectrum obtained by David Trowbridge, showing the spectrum of the target in the visible range, of course, Balmer lines, and showing first here the continuum by giant with its TIO absorptions. And one can detect the emissions of helium-2, thus temperature of about 50,000 degrees to produce this line by ionization. Here, He1 and there He1. So to replace the current status of Teyssier, here, first I'm sorry because I have a very nice graph of the equivalent width of H alpha with all the values detected by our spectra, but unfortunately I destroyed the result obtained with my Python code. So I will send you the tomorrow or this weekend. But here you have the equivalent width of H alpha. Of course, as we have a strong variation of the continuum according to orbital phase and the state of the system, it is clear that equivalent weights is not the best measure of the activity. But in the 80s and 90s of the last century, the values, the published values, were equivalent weights. So it is interesting to use the equivalent weights of H alpha in order to compare the common status of TCRB according to previous published values. Here is, one can see two active phases with an equivalent weight of H alpha of about 30, while during the very active phase, the equivalent weight of H alpha was a level of almost 60. Thus, we are currently about at this level. The flare detected in November 2024 was very short. Another one has been detected by a professional team and who produced an astronomer telegram, and this flare or activity of the system was detected, in fact, in January 2024, thus 2 months ago. The question is it really a new active phase or a short flare? Clearly, I don't know. Only the next observations will be able to decide in which state is the system. The last spectra shows helium-2, so it is possible that we are in a new active phase. I will conclude with the idea that we have produced a formidable set of data, and we continue. The idea is trying to obtain a spectrum by day, in fact. The resolution must be over 500, okay? If you can produce a fixed calibration of your spectra with V photometry obtained during the acquisition, this is perfect. Not mandatory, but excellent. You can produce also time series on H alpha. H alpha line, which is the most observed line in amateur programs, is not really the most interesting line. But in the case of TCRB, it is very interesting because we can compare the equivalent weights or flux, better, of with the historical series. If you have a small range of wavelengths, we recommend the H beta and He2 4686. And of course, if you have a UVX, the near UV range is very, very important and interesting. Photometry, I would say there are more and more data. Le model should be perhaps less, but better. One very interesting project is observing the flecking of Teyssier. As we have an equation through the boundary layer between the equation disk and the white dwarf, there's really a strong, very strong flecking, which may depend of the orbital phase, but also which can be in relation with the activity of the system. So if you can produce time series, this is excellent, with a duration over 2 hours, the exposure the shorter as possible with, of course, SNR over 100. The B band is the very interesting band because the flecking is more important in B. If you can go to U, it's perfect, but most of amateur observatories have not the equipment for that. And of course, check the quality with a check star in the field. Here's an example of flecking of H alpha obtained by our colleague Xavier Dupont with a very small aperture, only 66 millimeter lens, showing the flickering of no, not H alpha, B, sorry, correction, B flickering, and an estimation of the flickering using autocorrelation function, showing that dependently of the frequency, we have detected flickering. This is this curve. A not flickering star should have produced an horizontal line. So now I'm going to the end. When the nova outburst, clearly nobody knows, nobody can predict precisely when the outburst will happen. Very serious team with Mikolayevska, Ilkiewicz, say precisely that the active phase are not connected to the classical nova outburst. The active phase are just a period, a state of the system in which the accretion weight is increasing. But the problem is how can we obtain the accretion weight precisely from the observations, of course, the visual range, of course, X-rays, of course, there is a strong uncertainty. What we can say is that the nova burst will happen when, in fact, the pressure at the basis of the accreted envelope toward the core of the white dwarf will be sufficient to produce a critical pressure at which the thermonuclear runaway will happen. What is the problem? The critical pressure will depend on the mass. Sorry. The mass of the white dwarf, about the same that during the last Novae event in 1946. First, major parameter. Very sorry, got a cough. And the envelope mass, which is the sum of the remaining mass after the event detected in 1946 and the accreted mass since 1946. There are evaluations of the rate of transfer of material toward the envelope, but of course with a significant uncertainty. And to predict precisely the moment of the event, we should need an integration of the equation over about 80 years. We have not it. So I have a prediction. The Novae outburst will happen when the mass of the envelope will be sufficient to produce the critical pressure. This is, I think, but of course, Steve will precise, and so we cannot know when the Novae event will appear. Schiffer claimed from a comparison of the Lie curves, current Lie curve, and the Lie curve because last Novae event, that we are at the moment where Novae event can be produced. He proposed September last year. No, we have not seen the Novae event. This, I think, and once again, Steve will confirm we cannot know when will be the next Novae event. So we continue to observe the system, and we produce, in fact, I think, very valuable information with essentially the candency and the quality of our observation. Well, been a little bit longer than I wanted. Just a transition. I want to share with you my humanism. Well, Steve?
I'm here. Let's make sure that we can.
I let you
okay, you can hear me?
micro on the screen and so on.
Okay, so I'll start with this. This is the Italian version of Walt Kelly's famous cartoon of Pogo. We have met the enemy and he is us. I can't say enough in support of what François put up, and really have to urge all of you to, whatever particular political views you might have. Realize that what's going on now is an attack on something so fundamental that it goes beyond any of the normal boundaries of political discourse. We're seeing a dismantling of many of the tools that have taken several generations to build up, research efforts, community outreach efforts, public education efforts, universities that have grown organically over the span of the post-war years, and at an international level of cooperation that now is literally being torn apart. It has nothing to do just with what's going on in the United States. This is something that touches all of us. We're a community. I mean, you're from all over the place. That's the most wonderful thing about these discussions. You're the demonstration that what began as a gentleman's affair in the 17th century has turned into something which is genuinely a social good, in fact, a social necessity, and the one thing that binds us all together, regardless of our particular ideologies, that this is reality, and we're dealing with an attack on reality. So that's the only comment I'm going to make that's political, which is unusual for me, but I just wanted to support what François was saying. And again, to emphasize that by your participation, you've just voted with your feet. So now to go back to our regularly scheduled program. First, there is more than just an irony in this slide. We've been talking about T-Corbor for a long time, a lot longer than I think in some cases it warrants. So one of the things I'm going to try to emphasize, rather than what François has done in setting up the phenomenological background, I want to emphasize the physics that govern what you're seeing, and especially why the physical processes that you're seeing here aren't really all that unusual. And let me begin with one blanket statement. T-Corbor is a really nice system, large measure because it happens to be close. And by being about a factor of almost 3 closer than the prototypical system, ARAS Zoom, which has gone through several outbursts, not just one in the pre-CCD and photographic era, we have considerable information about the processes we will expect to see happening here. And so this becomes not so much a way of discovering, but a way of testing whether we've understood what the hell we're talking about. I really want to emphasize that it's very easy to play the hype game, which is going on now at an insane level. The only reason that we're talking about this system when we're talking about it is that it's been predicted to be in the process of preparing itself to go into a Nova event. And to emphasize something that François showed, that was based entirely, and I'll emphasize this, entirely on photometry. In fact, entirely on visual photometry. Now let's get this clear. Photometry measures the energy output in a band. It doesn't tell you anything about the dynamics. It tells you nothing about geometry, and it doesn't even necessarily tell you about structure, because when you have a system that's this large, something as simple as flickering on timescales of hours may in fact be affected by orbital modulation or light travel time effects and non-locality. So unless you have direct spectroscopic measures, you really can't figure any of this out. And that's the advantage of having this prediction sitting around, that it has gotten people's attention. There's an old uh, commonplace in American English that if you want to get a mule's attention, the first thing you do is hit it in the face with a 2x4, and once you've got his attention, then you can talk. So having the publicity that this is about to go off is something that's encouraged a considerable amount of work, freed up a lot of large telescope time. In fact, I'll just add the political comment, even though I said I wouldn't. Probably more time in the pre-outburst stage than should have been, than it warranted, and that should have been given, because other projects are not being executed for this. But never mind, we're fortunate. The Gaia observations put this at less than 1 kiloparsec. That makes it about a factor of 2+ closer than the observations indicate for ARAS Ophiuchi, which also has a longer period. This period is about 2/3 of a year, and ARAS Ophiuchi is about a year. That doesn't really mean very much. Again, the most important fact in this setting is that the symbiotic systems are novae that have the wrong companion. Okay? These are, in this case, white dwarfs that, instead of finding themselves in the normal environment with a compact star, a main sequence or near main sequence star as a companion, find themselves sitting next to a red giant. Now, this is like being on Earth, okay? That we on the planet Earth sit inside the solar wind. Okay, that's 10 to the minus 14 solar masses per year. It's 7 orders of magnitude lower than the mass loss rate from the red giant, but we sit inside that, and there is, in fact, an accretion that takes place. It's called the magnetosphere. We have an interaction zone called the magnetopause, and the whole of the heliosphere, which is the other way of talking about the solar wind, completely engulfs the Earth and all of the planets. On the moon, when the Apollo astronauts were actually bouncing around on the surface, they had left sheets of aluminum in which the solar wind was embedded. And so we even know what the composition is and can compare that with the solar corona. Okay, but this doesn't have any dramatic effect on the evolution of the planet, other than over the course of time, if there were no magnetic field to assist in the stripping of the planetary atmosphere in the way it did on Mars. But the key difference is that in these systems, however the mass is delivered onto the white dwarf, once it's sitting on that surface, to emphasize what François had outlined, it doesn't matter how it got there. So for the moment, if let me switch screens so I can draw some cartoons. And as always, please, if anything I say doesn't make sense, or you'd like something amplified, just stop me, okay? We'll hope this works. Okay, so what you're looking at is, on the white dwarf, a layer that's accumulating on top of the surface. So here you have either principally carbon and oxygen, or if it if the star from which the white dwarf has emerged, since this is the core, the remnant core of the star, if it has gone through a full alpha processing, instead of stopping at oxygen, it will go beyond that and into neon and even heavier elements. Now, that's an inert core in the sense that it has no nuclear processing at all. It's the result of the object having been born in the core of what was a star that's gotten stripped. Now, the fundamental difference in the white dwarf in the compact recurrence like T-Corbor or USCO is that when you have a binary with a period of a couple of days or a week or a few hours, in the case of USCO, it's a little over a day. In T-Pix, it's a bit over an hour. The white dwarf is always going to have the same radius in equilibrium. It just depends on its mass. And the only reason for that is because the equation of state, I'm sorry, the law that governs the internal pressure structure happens to be supported entirely on the backs of the electrons, which, as I'm sure you know, are in this case equivalent to a cold gas. So the thing that's important to keep in mind is all white dwarfs are basically the same. It's how they get there that's the problem. If you've got two stars that are wide apart, say one of them is orbiting at the distance of the Earth from the sun, then you don't care about the evolution in the sense of mass exchange, because while the star that eventually strips and becomes the white dwarf is evolving, it may be far enough from its companion that they're simply orbiting each other. But there's no mass exchange other than maybe a bit of accretion from a wind. On the other hand, in the compact systems, you can't get the white dwarf to be an oxygen neon core if you haven't already had the star somehow able to get to that stage in its evolution. And to do that, it has to be effectively a supergiant. So you're dealing with a system that has a period now of, let's say, 90 minutes, as in T-Corbor, but what you had to have had was a system that looked a lot more like a symbiotic. Okay? Otherwise, you would never have been able to build up that core. Now, after you do that, and that's, we can talk about that in a couple of weeks when we're discussing mergers. But the thing that's important is once you have the white dwarf, whatever you dump on this layer, whether this is hydrogen or helium, or we'll say, let me write this as zeta solar, which just means ordinary metal-rich material. As that stuff accumulates, the compression, because this is a compressible medium, in the base of that layer can eventually reach the point of triggering nuclear reactions. Now those are going to be moderately slow. That is, you have in this zone, you have hydrogen. In other words, you have protons. The electrons are not going to take part. They're just background pressure. They're also not going to heat. The ions do. So the protons are going to have temperatures that are in excess of like 10 to the 7 K when enough of this garbage has piled on top. And once that threshold is reached, then it's exactly like triggering nuclear reactions in the core of a main sequence star. That is, you've got some carbon around. In fact, in this interface, you have, it doesn't even matter if it mixes. It doesn't matter how it mixes, just as long as there's a little bit of a trigger, it's effectively lighting a match and starting a forest fire. That once the first reactions begin in this interfacial zone, however that zone has been mixed, that immediately becomes exothermic, which means that the energy is being released from that zone, the temperature goes up, and the ions heat. The electrons don't do a damn thing, but the ions do. And because this zone is so thin, I mean, okay, let me put it differently. A white dwarf is a star with the mass of the sun and about the Earth's radius. So you're dealing with a surface gravity that's 4 orders of magnitude larger than on the Earth. That's important because buoyancy, that is convection, depends on gravity. It's going to be much more vigorous the higher the gravity is. I know that that actually sounds almost paradoxical, that things move faster upward because of gravity, but remember that convection happens because when you raise a parcel of the material, so at this interface, if you have something that goes up, this has to displace material downward, and so it's releasing potential energy. And that depends on gravity. So the higher the gravity, the more energy is available. The result is that this zone starts to create tongues and fingers and begins mixing. And once that happens, things literally run away. That the temperature goes up, the mixing increases, the rate of burning goes up, the temperature goes up, the rate of burning increases, and the whole time the ions are getting progressively hotter, but they're not supporting the medium. The ions, the protons, are 2,000 times more massive than the electrons. So they're behaving like an ordinary gas, but they don't contribute to the pressure. On the other hand, the electrons do, and eventually, because this isn't a process where the electrons just stand around with their hands folded, saying, oh, I'll wait until something happens. They are getting heated, but they're still being dominated by so-called quantum effects. That is, they simply are a degenerate gas until the temperature gets high enough, and that creates the explosion. So there are 2 pieces here. This is universal. All novae, recurrent, symbiotic-like recurrent, or classical, are exactly the same physical process. That is, you're triggering a nuclear reaction under conditions that do not mechanically adjust to the thermal input. And the result is an explosion. Once you do that, the amount of energy released is what determines the subsequent evolution of the nova event. Now, let me go back for just a minute. I said that all of this is happening on the surface of the white dwarf. In a way, that's a lie. It's happening in the outer layers of the dwarf, but this is not what you are seeing sitting at your telescope here on Earth. Okay? You're seeing something even higher up that's the result of the radiative transfer through this zone. So you see the emission from a photosphere. While this stuff is accumulating, this is not triggering at the surface. That's a term that gets used far too oh boy, that's a bad pun, far too superficially than we should. Um, what's actually happening is that in the earliest stages and before the triggering of the reaction, as this layer is building up, it's compressing. And compressing, it's heating. Heating with an outer boundary condition that may be what Francois referred to as a boundary layer. In fact, it certainly will be. But there's also simply space. And so there's a temperature difference. And the result is there's some radiative process here, diffusion, that brings energy to the surface. And that's what you see. And that's why I said the photometry doesn't tell you what's going on, because everything at the surface and that you're capable of seeing is being driven by processes that are deeper in the white dwarf and also in the accretion disk. Because of the triggering, it isn't something that goes like a fuse. Let me make this clear. It isn't that you're accumulating a layer and then somebody comes along and pushes a button and the thing blows, or a plunger like the classic sequences of blowing up a mine. What's happening is the layer is increasing in temperature over the entire period of accretion. There's a critical threshold, but that critical threshold is reached and passed in a time that is much longer than the accumulation time that we're seeing now. Okay, the light curve changes, things like the flares, those are happening on timescales of days. The accumulation of this layer takes decades at the rate at which it's accumulating. The other thing to keep in mind is that a good deal of the light in the visible is not coming from the white dwarf because the damn thing is so hot that if you looked in the X-rays, if you could see it in the X-rays, that's where you'd see it. You certainly see it in the ultraviolet. And I'll talk a bit about that later. But the dominant emission lines here are coming from regions that have absolutely bloody nothing to do with the surface of the white dwarf. The flares may be material that happens to accrete onto the white dwarf, literally fall onto it a little bit more at a time than other times. There may be some other cycle that's delivering mass differently over the course of years. I wouldn't be surprised at that, since we don't understand what's going on in the red giant. But to then say that we can use that, the similarity of the light curves, to predict the explosion without knowing what the mechanism is, I think is kind of black magic. You have coincidences. The light curves do have coincidences, but I'll emphasize that the light curve is not the nuclear source, and it's, in fact, something very different and ambiguous. Now, the other part of this is what the system looks like up close and personal. The other side of Francois' diagram, that you have the white dwarf, and around it, you have an accretion region. It's important to emphasize that this accretion region, and I'm not drawing magnetic field lines here, that this region is hot and stratified. And so you're seeing here a kind of, donut, bagel, whatever your ethnic preference happens to be. This layer is built up because in the system here, you have a wind that's blowing, and this system is orbiting. This is the red giant. The separation between these is a few stellar radii, and this wind isn't spherical, so it's going to be accreted by the white dwarf. This is exactly the picture that many of you know from symbiotic stars. The fact that it's orbiting already means there's angular momentum in the system. So you're going to form a disk. Over time, the disk is going to form around the white dwarf. It will reach some typical maximum distance at which the pressure from the wind kind of truncates the disk. We know that from observations. But that's it. Now, if something happens that, for instance, during a stellar cycle, if this is magnetic, it happens that there's a passage of a coronal hole in front of the white or toward the white dwarf. This is very important because the structuring of the magnetic field on the sun changes the way the solar mass is lost through the wind. That the fast wind comes out of coronal holes, which are intrinsically cooler. And when I say fast, I mean a factor of 2 difference. But again, this is a very low density region, and the magnetic field is also fairly weak. We don't know anything about the magnetic cycles of these stars. And it's almost certainly there is a dynamo somewhere inside this bugger. So that's certainly going to modulate the wind. Is that going to be enough to completely change the transmission of material? Let me make another point. In the solar wind, the velocities vary between 400 and 700 kilometers per second. Okay? You got that? In the red giant, it's a factor of 10 lower, which means that at a distance of 1 AU, you have material coming at you that's practically walking its way compared with the solar wind. So although this is a very dense wind in comparison with the wind from a normal main sequence star of the same surface temperature or a solar type star, it's still very slow and stratified. And so if something hiccups on the surface of the star, it's not 8 minutes later that that's going to arrive. Okay? That when we have differential streams, there may be much larger differences between the wind and the poles, the wind from regions that are open or closed field lines. Again, we don't know this. The models that have been calculated for the mass exchange haven't included the effects of dynamos because right now it would be highly speculative. But the one thing you can be dead sure of is that the formation of the wind is going to be thermal. It's going to be driven by the normal mass loss processes from the red giant, enhanced by the presence of the companion, not exactly at the level that we see from normal novae, which have companions that fill their Roche lobes. So it's not that kind of stream, but it's a focused flow in a system that has an orbital angular momentum, and consequently, it's falling down a drain and it's going to form an accretion disk. Okay? And that accretion disk is going to be resident for the entire time until this thing does something really unpleasant, like exploding. Now, everything that I've said so far is almost independent of what the companion is. As long as you have a mass source, you could actually have the white dwarf moving through a background molecular cloud, and if it accreted enough material, it would do the same thing. Fortunately, that doesn't happen because one, there aren't many molecular clouds, and two, white dwarfs usually don't go through them. But this is basically the same thing. It's only the rarity here. Now, having let let's go to go back to the original screen. So before going on, I really want to thank the people who have been courageous or stupid enough to work with me on over these years on this stuff. Um, Alessandra did her thesis on the comparative UV and optical behavior of all of the known symbiotic recurrence for which there was even a remotely useful data set. Katia Genovale spanned the initial period with V407 Cygni. Paul Kuhn is the master of the GRISM on Swift and probably not probably, the person most knowledgeable about things spectroscopic in that part of the UV. Um, I will just say, and then there's Elena Mason and Kim Page, and obviously François, and my longtime and close friend and collaborator, Glenn Walgren, who is one of the ones who is on the front line in all of this, being at Space Telescope Institute in Baltimore and involved with the calibration of instruments, spectroscopic instruments on JWST. You can imagine what the world has turned into for him. So what we're going to see. This is a STIS spectrum. These are ultraviolet lines. The carbon-4, magnesium-2, and iron-2, 2600. I'm only showing this to give you an idea of how complicated the system is going to be. This is the quiescence spectrum. It was taken a couple of years ago. The carbon-4 is a line that indicates, if it's thermal, temperatures that are characteristic of the transition region of the corona. So several tens of thousands of degrees up to a couple of 100,000 degrees. The thing that you can see in this is there's a doublet, and well, actually, this is the carbon-4 line. And what's more important is the doublet is 1548 and 1550. The ratio here is the same as you would predict for an optically thin transition. You also see that it's very narrow, exceedingly narrow, that if you insist on doing full width half maximum, rather, we're dealing with something that is only like 50 or 60 kilometers per second wide. That's the red giant wind. Now you might ask, maybe? You have a red giant. Francois showed a spectrum that was chock full of molecular lines, so this thing looks like Betelgeuse. What the hell would carbon-4 be doing there? This requires an ionizing source that's beyond helium-2. And the simple answer is, that's right. That's the effect of the white dwarf. Not that there's a shock. It's simply hot. That is, it has a strong UV radiation field, and a portion of the wind is ionized. And there's also a higher velocity component, and you see something very important here. The orange line is magnesium-2, which is a characteristic chromospheric line. And you'll notice that the green line is iron-2 at 2600. Now, I chose that one deliberately because it's one of the stronger interstellar lines in the spectrum. This has nothing to do with the star at all. This line of sight absorption from the interstellar medium. And you notice that the green line and the orange absorption agree precisely in velocity. In other words, the magnesium is not being absorbed out by the wind, but the carbon is. You see the P Cygni here. That's the result of the wind. So you've got a region that's ionized, highly ionized around the white dwarf. There's also this emission, which is partly scattering and partly thermal in the magnesium wings that agree with the carbon-4 wings. Again, that's from the wind. That's the neutral or nearly neutral part of the wind. But there are two different components, one of which is interstellar, that won't vary, and the other of which is stellar. Another comparison, the green line is again the carbon-4. The silicon-4 doublet is shown in white, and that's down here, okay? And then the carbon-3 for intercombination line, one that's formed at very low density, is shown in red. And again, you see that the highly ionized species, 3 times ionized silicon and carbon in the wind, are showing this p Cygni absorption that's not at the interstellar value. And then there's this line, the carbon-3. This is a line like in a planetary nebula that's formed only at low density. It's highly ionized. It requires over 40 electron volts to get you there. So the the carbon-3 and the carbon-4 are simply 2 ions of the same element. Okay? I hope that makes sense. You see that this line is telling you what the system velocity is. It's slightly displaced from 0. You see that the peak here corresponds to roughly the midpoint of the wings of the carbon-4. And again, that's the wind. And finally, the most highly ionized of all of them, the nitrogen-5 line, which in this case is this line. Okay, it's a doublet, but I'm showing only one of them. And you see that this consists of 2 components. One is shifted relative to the carbon-3. Okay, it's sitting on top of roughly the region where the absorption was coming from in the others. I hope if this is confusing, I hope it is, because what you're seeing here is the 3-dimensional structure of a wind. This is like looking at a tomogram. The individual ionic species are there only because they're being ionized, but you're seeing something that isn't necessarily along your line of sight. And I'll get back to that in a few minutes. So this is really telling you something 3-dimensional. Now, keep in mind, this was a snapshot. It's only one spectrum taken before anything was happening, but it was taken during roughly a period of normal activity. Now, this doesn't mean that this is what the quiescent spectrum looks like. This is simply what the state of the system is. The broad wing here is almost certainly the accretion region. The narrow region has nothing to do with that. Now, the next system, so that's setting up T-core Bohr. We're going to come back to that, but I wanted you to see what the system looks like now. There's been an enormous activity in the last year and a half getting spectra getting data, including observations that have been done with ALMA, with the VLA, SWIFT. I think there may even be a Chandra pointing. I'm sure there's an XMM pointing. It's wonderful to have this characterization of the system before it does anything. But one thing has to be remembered before I go on. The last outburst that was observed for T-core Bohr was in the 1940s. That was the Stone Age. It was remarkably clever in the way that things were understood, But you've got to remember that all of that data was uncalibrated in absolute flux. The only thing people had was photometry. And to make one very minor correction to something that François said, the optical light curve that we're talking about now is in UBV. The UBV system hadn't yet been invented in 1946. Okay? So you're looking there at photographic magnitudes and non-standard filters. So you don't know what the effect in those filters was of the emission lines, whether or changes in the illumination of the visible hemisphere or even orbital modulation. It's a fundamental limit that has to be faced if you're doing morphology of light curves. It's like doing morphology of spectra. If you're not using the same instrument, forget it. You can't do a direct comparison unless you have some other information to tell you what's going on. And we don't. So the behavior is similar. No question about that. You see the orbital modulation. You see the effects of the wind and the accretion, but individual features cannot be interpreted from that in the way that what I was just showing you allows you. Now, the system I want to do a comparison with is, actually, I'm not sure why this one isn't showing, but okay, this is what I was looking for. The top spectrum is a UV spectrum taken a very long time ago, in the 80s. This is a low resolution IUE spectrum, so roughly the equivalent of an ALPI 600, except at 1600 angstroms. So what you're seeing on the top spectrum and the bottom spectrum are the same star. This is T Corp. Okay? It's simply taken a few months apart. This is also T Corp, except that this is what happens to the top spectrum when you look at different directions through the wind. So this is a simulation of what here what here was an observation. In other words, if you take this spectrum and you have orbital motion and you're looking through the red giant wind, in other words, exactly like watching a sunset, that's what you're going to see. When you're on the near side, you'll see the emission lines. When you're on the far side, you won't. Okay? That's why I said this is more complicated than it seems. It's three-dimensional. So the orbital parameters in normal classical novae and compact recurrence won't produce this because the atmospheres of the companion are so compact that it's exactly like watching an exoplanet eclipse or an ordinary binary eclipse. There's a little bit of limb darkening, but nothing else. But here, you have stars that are separated. Now, please keep this in mind by an astronomical unit in a wind that has a path length of several astronomical units, different depending on which side of the orbit you happen to be looking at. Okay? So you can completely change the visibility. You would say, looking at this, that this was not a flare spectrum and this was a flare spectrum. Not that that's necessarily what's happening in the optical, but you have to be careful with these interpretations because at low resolution, You can't see the absorption that I was just showing you at high resolution. Okay? This is the garbage that's producing that absorption line on the carbon-4. So another example of that is this really beautiful result from the X-rays that by sheer chance, the, the symbiotic recurrent RSO was observed in outburst in 2006 and 2021 with the same satellite, SWIFT. It's just an astonishing piece of luck. Also, it's an amazing piece of luck that Kim Page was the one who did the data reduction. But the thing that I want you to notice is that there's an essential difference between the behavior of the 2006 and 2021 eruption. Not in the long term. Here, they're virtually identical. It's this part. That's the orbital modulation. That because of the phase at which the explosion occurred, it was about two-thirds of a period, about half a period different. So in one case, you were looking through the wind, in the other case, you weren't. It's not that the source turned on differently. It's that the smog cleared. Okay? It's essentially the same result as you're seeing here. Again, in the interpretation, if you have high enough resolution in your spectra, you'll be able to see this because the lines from the red giant are going to be very narrow by definition, unless something hits them. So, okay, we'll get back to this. I have to show this as a way of not deliberately confusing you, but this is the kind of time series that you're going to be able to get for T-Core-Bohr. And I want you to realize that, again, there's nothing particularly special about T-Core-Bohr except that it's going to be very bright and you'll be able to calibrate it, and it's happening in the modern era. Now, if everything, I should have added, if what we understand from these other systems applies, and we think it does. If it doesn't, we'll have learned something. The sequence that you're seeing is an ensemble of lines in the symbiotic recurrent Nova V407 Cygni in its 2010 outburst. Actually, it's a stretch to say this thing is a recurrent because this is the only event that's been seen. But when you've got 5 systems and they all look alike and they're recurrents, and then you have one that looks like it and it's not known to be a recurrent, it's a pretty good bet that it's a recurrent and you just didn't see the previous outburst. It also isn't a particularly bright system. And one last comment about recurrence is especially with T-Core-Bohr, because although it's been touted as the brightest nova of our lifetimes, that brightest nova is only going to last a couple of days. So either make sure that you don't fall asleep, that the weather is perfect, and that it doesn't have a moon or a sun constraint. Okay? Recurrence doesn't just mean that it's occurred twice in human lifetimes or in somebody's lifetime. It also means that somebody saw it. Okay? Um, if it if it goes off at the wrong time of year for the northern hemisphere, and there's nobody in the southern hemisphere because everybody is in a different mindset than building telescopes, that's it, you know? You won't know that it's a recurrent. Okay, so with that polemic, the top line, each one of these is a different line read from left to right. It's a time series showing the spectroscopic development of this nova, age alpha, beta, gamma, delta, helium-2 4686, and the helium singlet 6678. There are two things to notice. The first is that at the very beginning of the outburst, the velocities, by the way, are ranging from about minus 1,500 to plus 1,500 kilometers per second, but this is from minus 1,000 to plus 1,000. This is already well into the outburst. This is like a month later. But you see that there are two components most easily seen on lines like H gamma or on H beta. One of them is this very broad line that, trust me, is not a Gaussian. And then there's this other line, which is a very narrow component, the same narrow component you were just looking at. And this is what the fundamental difference is between a symbiotic nova and a classical nova that we've already talked about at other times. This is an explosion inside an atmosphere. It's something that unfortunately you all are familiar with because every time you've seen a film of the initial stages of a nuclear explosion, that's what this looks like. The first stage, the very first step. And now let me switch screens to go back. The very first step is that out of the explosion, ignoring the ejecta, there is a light pulse that moves out into the wind of the red giant. There's a density gradient in this background where the highest densities are in the direction here of the giant. So this is high and this is low density. The low density material has a low velocity, but it's terminal velocity and it's expanding outward. And the high velocity material is toward the red giant. And so there's going to be a region that's ionized at any moment that looks something like this as a boundary. And as this pulse propagates outward, you're going to see progressively more of this narrow wind appearing. Lines that are going to show up are like O2, helium 1 and 2, mainly the helium-2, if it's a hard enough flux, obviously the emission on the bomber, etc. lines, but also O3, O1, iron 2 plus others. In other words, anything that can be formed in a low density region from a pulse that has maybe 100 electron volts as a characteristic energy. Okay, just straight photoionization. Difference being that it's a pulse. And so it's a little bit harder to calculate what's going to happen. But the region that's going toward the giant is a higher density region. It's also got a different velocity. And it's going to have a different velocity relative to you. It's a smaller volume. So you're going to have contributions from many different regions here that have different velocities. This is before, let me emphasize this, this is much before the shock from the explosion. And that's the critical difference between a classical nova and this system. Everything you're seeing here is because of the envelope. Everything you're seeing is because it's embedded in a background. In classical novae, the explosion of the ejecta goes into nothing. It's just big, empty space. And so you've got this garbage like fireworks that are just fragments going out into Never Never Land and cooling. And so you see the development of the absorption lines in a very characteristic way and of the emission lines. This is totally different. You have here literally a nuclear explosion analog inside an atmosphere. The atmosphere also has another, has an, the atmosphere also has an abundance. And that's important. In a classical nova, the explosion of the white dwarf expels material without any subsequent mixing event once the material is in free flight. Okay, by that I mean once you kick the crap out into the interstellar medium, it's just moving out into what is in effect a vacuum. Okay? So every little brick, every piece, every fragment of the ejecta maintains whatever was frozen into it. It's literally nuclear waste disposal, that some of the fragments are going to be a little bit richer in oxygen, others a little more carbon. Perhaps some will be depleted in nitrogen or enhanced in nitrogen, but that's not going to change. This is different. This is a snowplow. This is a region, an ejecta that is interacting with and absorbing the wind. So let me go to another slide to explain something about the physical process of propagating a shock, because I think that'll help. So uh, consider that somehow you have a piston that's moving into a canister, or in this case, into the wind. So we have here a front that's moving here as well. It could be a set of fragments. It doesn't matter. I mean, you've all seen films of chemical explosions, like the one in Beirut during the post-pandemic years, or nuclear tests like the Trinity. Um, I mean, all of the things that Oppenheimer got wrong in the film. Sorry, I had to say that. So we'll have here some velocity, some radial velocity of the ejecta. And out here, there's stuff that this is expanding into. And so it's the equivalent in the frame of the shock of this stuff being compressed here and accelerated, so that behind the shock, there's a region of higher density that's moving outward now with the shock, but not as quickly, because it's been overrun and accelerated, but not as much as the shock itself. The important difference is that material came from the wind, not from the explosion. So while the nova may be producing carbon, nitrogen, oxygen, perhaps sulfur, perhaps silicon. Okay, so this is from the nuclear processing. The red giant is going to have hydrogen, helium, and then CNO, but a hell of a lot less carbon than the white dwarf had, and certainly not as much oxygen. Okay, so the result of this is mixing. The composition as this material expands changes. If you see the spectrum of the ejecta, the fast material, in the first couple of days. It's not going to be the same by the time that material has been expanding for a week into this background. It's going to have progressively more solar-like abundances. Now, I say this because it's extremely difficult to understand the dynamics of the explosion without asking questions about the nuclear processing. And the only way we understand the processing is by looking at the abundances in the ejecta in classical novae, because once the explosion occurs, that's the end of the nuclear reactions in the ejecta. You simply freeze it. That's why I said this is throwing its nuclear waste into the interstellar medium. Here, that's not true. This is absorbing. This is the material moving out into a background with different densities and different abundances. The other thing that happens is that in the classical nova, the expansion of this front into nothing means that it's simply cooling. The energy was finite, so the pressure has to be dropping internally, and the temperature drops, and you see a characteristic evolution of the spectrum. That is, it goes from fairly dense, relatively cool material to highly ionized because it's illuminated by the white dwarf, but simply expanding and continually expanding at constant velocities. You don't see that here. The velocities decrease in time. They physically decrease. You can tell that from looking at different transitions. And this is essential, the shock produces energetic phenomena that you never see in classical novae. To wit, the temperature back here can get to higher than 10 to the 8 Kelvin. You can have turbulent waves moving out ahead of this that can accelerate particles, and so you can have cosmic rays being created here. You get radio emission from synchrotron and extremely strong X-rays that then ionize this whole material. So as this thing is expanding, it's not only changing its composition and changing its mass, which is another problem, it's also illuminating the background with a different spectrum as it evolves. Again, if this sounds complicated, it is. And because we have so few events that have been carefully observed and observed with modern equipment, this becomes essential. Before I go on, you might be asking yourselves, with all of this technical detail, why the hell does anybody care that much about this? There's one reason I can give to a question like that, if it's occurred to you. One is, of course, it's neat. I mean, how many times do you get to sit, how many times do you get to sit a kiloparsec away and watch a nuclear explosion? Um, Sounds like something out of The Day the Earth Stood Still. But there's another side to it, which is much more fundamental. The velocity that this front has is several thousand kilometers per second. It's going into a region that has a density of like 10 to the 8 or even higher per cubic centimeter. This is exactly what happens when a supernova hits a molecular cloud. It doesn't matter that this is 10 to the minus 7 solar masses instead of a solar mass. It doesn't matter that the energy involved here is so much lower. This is hydrodynamics, damn it. This allows us to actually watch, dissect in real time something that we only see in snapshots looking at the supernova. Because by the time we see this kind of event, they're so far away and the physical scale over which we see the changes so large that even with an appropriate pension plan, you will not live to see that change, with very few exceptions that are much earlier stages in the expansion. So this allows us to see hydrodynamic phenomena that are as universal as the process of a wind emitted by a supermassive black hole, a supernova remnant in the interstellar medium, or the outflow from a galaxy in the early universe into the background halo. It's just straight hydrodynamics. Again, once the TNR has occurred, once the explosion has occurred, you don't give a damn. It just freely expands. And then the evolution of the background takes over. So now going back to a screen change here. So going back to the rogues gallery, um, this sequence, the helium-2, is what's telling everything. You'll notice that it's kind of asymmetric, like skewed, kind of like triangle. This is because of seeing the shock at an angle. That this high velocity is the part of the shock that's moving outward, and this compressed region is the part of the shock that's moving inward. In other words, we're getting a three-dimensional picture from one line profile. This is what's confirming that the explosion is actually occurring in a wind. This is a line that's formed by recombination, so it's very sensitive to the background density. And it's giving you the profile of the wind. Then all of these narrow lines are the part of the wind that hasn't been hit yet by the shock. Okay? Those narrow lines are from the unshocked wind, which means it lies outside of this. Some of it may actually be shadowed. There's another effect that was seen, and this I'm hoping we will see in T-Core-Bohr. This is a better sequence. Going from the bottom to the top is the sequence in time. This is the sodium D line. The double line, these two, are from the interstellar medium. Okay? Leave them alone. What's remarkable is this emission line and this absorption line. This was never seen. First, there's an emission at sodium, okay? That means that there's material in the shock that gets down to temperatures as low as 20,000 or so degrees. Otherwise, you wouldn't see neutral sodium in recombination. But what was strange was that this absorption line appeared at the same time as this little glitch of an emission line, and it's symmetric. It's a light. This is the effect of a light propagation. This is the actual pulse going out from the white dwarf in the explosion, and it's recombining. So the part that's in your line of sight is showing absorption, and the part that's in the other direction is showing emission. And you can be sure that that's happening because you can see it on the two lines. It's just a detail. It was pure chance that we saw something like this. It was totally unexpected. But this is, again, the kind of thing that says you're looking at a medium that has very strong changes in density and velocity within its structure. This graph shows Okay, let me come back to this before we're finished. This is going to take a little bit of explaining, and I don't want to overwhelm you, at least not yet. Um, this is another example of showing the effect of the background in absorption. These are UV spectra taken of ARAS Zoom during the 1985 outburst. Um, the only thing that you can notice here is that you have all sorts of structure. This is helium-2, and this is oxygen-1. It's just showing that over time, the lines are going to change and they have multiple components. I just want to keep emphasizing this. You don't see this in classical novae. And consequently, you can't use the classical nova as the structural paradigm for interpreting this. Um, well, this is what you're seeing. That is, you have a shock within the red giant wind. The white dwarf here produces a hot bubble. That bubble is not spherical. It's compressed and also extended off the plane. It may even show an aberration effect. It depends on what happens with the orbital period. But this region is ionized. This region is ionized. What I wrote here with the I in script is the ionization region. So all of this is the ionized wind. This portion behind the red giant not only is never going to be shocked, but it's never going to be ionized. It's actually shadow region. Again, you don't see this in classical novae because you don't have this kind of volume. But if you are looking from this direction or this direction, you see different results. As it happens, in 2006, we were looking in this direction. So it was a clear view to the white dwarf. And the result was the X-rays turned on faster because there was less absorbing material than here in 2021. Otherwise, there was no difference between them. And I come back to that last slide. You can determine where the shock is by looking at the propagation of, looking at the change in the velocities of the wings of the lines. You got an idea of how the ejecta are moving outward in the red giant wind. And then you can see when different lines appear that are telling you something about the formation. Specifically, that low electron densities come from certain transitions. They're sampled by forbidden lines, and high density transitions, permitted transitions like recombination are sampling the high densities. If you have low density, you see the forbidden lines, but the permitted lines will be weaker. If you have high density regions, you won't see the forbidden lines, and the permitted lines can be stronger. And so this is just an indication of how the tracer of electron density changes over time in all of the novae that Alessandra studied, which was 3 different outbursts of ARAS Ophiuchi, 2 of V3890 Sagittarius, which is one with a Myra companion, V745 SCO in 1989, and then RSOF in 2021. And the thing that's striking is they follow exactly the same evolution curve. All that means is you're sampling the environment. You are not sampling the shock. It's that you always hit about the same region at about the same time with the same characteristic time scale for either recombination or line formation by collisions. But the important thing is you don't see this in classical novae. You only see this in this kind of system. If you were Methuselah and you could observe this in supernovae, you would get this for the supernova distribution in, say, the galactic center. Just as a side comment. In V407 Cygni, just to again give another example, this is something like the plot that François showed for the flare. This is a comparison between the forbidden nitrogen 2 line, nickel 2 line, which is just a forbidden line. I mean, never mind, and a recombination line from helium. So the forbidden line increases as the emission from this larger and larger and larger volume goes up, and as the ejecta, which are responsible for the helium, slow down, you see the decrease in the helium emission. So one of them is rising, that's the low density, and the other is falling, that's the high density region. The lines also change their shape over time. This is, again, V407 over the same time scale. This is covering a period of almost a year. So from the first appearance of the forbidden iron 7, which you see is a very narrow feature, okay? Now, let me make this clear. This is a line that requires, for its formation, 100 electron volts. In other words, you got to illuminate this by something like X-rays. This isn't temperature, people. This is the wind of the red giant being ionized, and then, bam, it gets hit by the shock. And that's what you're seeing here. There's the shock profile. This is literally material being overrun. I hope I've given you the enthusiasm with that one, because I don't know anything that I can show you that's that's better preparation for and more remarkable than what you're going to see in T-Corp. This will happen. You're going to see this change. And you are literally watching a three-dimensional structure by looking at a single bloody line profile. Okay? This is a line that is not formed hot. It's formed photoionized at the beginning, and then it's hot. And in fact, as the ejecta expand, you see that there are different shape changes. Again, it's decelerating in one direction here, and it's accelerating in the other direction. This is exactly what you saw on the helium-2 line. So again, it's three-dimensional structure. So the bottom line is, because I'm sure you're tired by now. The phenomena that are going to be exhibited by this outburst will probably be covered by more individual projects and more instruments covering more of the spectrum than any such event in the last century. We'll certainly be able to see this in every wavelength region from penta-electron volts to ALMA and centimeter radio wavelengths. We're at a unique position now that we weren't in with RSOF, that this is actually observable not only from both hemispheres. RSOF was a southern hemisphere object, and so it had limited visibility in the north compared with T-Corp. T-Corp can be seen from Chile. We've already looked at it with ALMA. So it's been imaged. And it also has coverage with just about every radio telescope on the planet. In addition to which, there are satellites covering the UV still operating in space, that is STIS and COS on HST, are still functioning. So we've got a chance of actually getting UV high-resolution spectroscopy. The entire X-ray region is extensively covered, including high-resolution spectra on XMM, for which this will not be too bright. It'll be observable with Gaia, and just about every instrument, actually just about every instrument in space will be able to look at this thing, including JWST, for which it's actually going to be too bloody bright, at least at the beginning. So whenever this goes off, the advantage now is that people have been primed to anticipate it. What I hope I've been able to convince you is that the processes that it's going to display are those that we can very readily understand and exploit, and that the uniqueness of this object is simply going to be the richness of its data set. As a last thing, at the risk of boring you, I'm going to repeat, there is nothing special about this object. That is perhaps why it's special, that we have so few of these to work with, that the fact that we now have a probe that we will be able to study with all of the tools that have been developed for the other systems will finally allow a real deep compare and contrast. Astronomy works often, not in the current generations, but at least in my antique days, in the deep study of single objects that happen to show unusual or illustrative characteristics. It's not just puzzle solving. It can degenerate into that. But the other is just by sheer bloody chance, you're seeing a phenomenon that you haven't been able to see before. That when you see a cosmic puzzle, it's not that you're trying to figure out what's going on, it's that you're seeing something happen that is manifesting itself in a way you haven't seen before. Okay? It's like running an experiment in the laboratory to create some chemical and having instead some little thing in the bottom of the petri dish smiling at you. You know, it's something that you didn't expect to happen. So you've learned something. With these systems, we have the big picture. With Novae, we have the big picture. We're going past that now. These are now tools. They're not laboratories because we can't control them, but we can deeply study them. We can follow them and prepare the individual analyses in overlapping ways to reveal the underlying physics of objects that will show similar phenomena and that we will never be able to study in this way. That's what's waiting for us whenever this thing goes off. So I hope that that's made a few things clearer. If there are any comments or questions or annoyances, insults, please start. Thank you.
Steve, I'd like to thank you for that very last slide. I had seen profiles of that ionized iron line turning into a flat top and never understood what it was. Thank you.
Ooh, I'm glad. Actually, that's always going. Frequently, for example, when people see double peaks, the first thing they do is fit Gaussians, and I've never understood that because Gauss didn't look like that. But the other thing is a Gaussian profile, or any profile, in fact, individually fit, is making an extremely strong statement about the origin of that profile. It's a continuous medium. And the reason you see different profiles, as I was showing on different lines, is because they're probing different regions of density. That you can have the same velocity structure, that is, you can have a single shock for the iron that is also the same as helium, but the iron is going to be formed only in the low density regions. where the helium is going to be formed by recombination in regions that are systematically too dense to show the iron line. So if you try using only one or the other, or you only use equivalent widths, and you don't look at the profiles, you've thrown away the one piece of information you've got, which is the density stratification, which in this case is everything because it's a terminal wind. So if you know how the density behaves, you can determine how much mass that star is losing, you can get its abundances, you can understand how it is accreted by the white dwarf. All of that suddenly becomes available to you just from that line profile or from the profile comparisons. Now, you see the same thing in freely expanding ejecta, but there you don't see these asymmetries. And again, you see different regions contributing at the same time. The outer portions of the ejecta are, if it's completely ionized, the outer portions are going to show the forbidden lines, the inner portions won't. The inner will show the recombination, the outer portions won't. So the recombination lines are going to be narrower than the forbidden lines. Okay? Now, that's in the freely expanding ejecta. But here you're slowing the shock down. So the higher density material is the stuff that's immediately behind the shock. And the lower density stuff is now coming out the back. It's already flowed through the shock. The beauty is over time, you can see the way this changes because the shock is moving inside the red giant wind. You would see exactly the same thing if you look at supernovae in the ISM. But to see this stage, that is where you have what's referred to as a spatzneve, a snowplow phase, where the shock is now radiating and accumulating material at the same time. You would have to wait about 100,000 years after the explosion, somewhere between 30 and 100,000, for the typical interstellar medium to hit the same stage. Here, now you'll hit that stage within about 2 weeks.
It's great. Other questions, guys?
Yeah, yes, maybe I have one.
Please.
Yes, I would like to know if we are able to explain the mechanism by which accretion is not increasing in a continuous way till reaching the critical point. Why
Huh?
is there some decreases and so on?
When was the last time you took a bath?
Yes.
Okay. When you've let the water out, does it flow out steadily or does it occasionally bubble?
Yes, it bubbles.
You got it. Make that material accrete at a few thousand kilometers per second. Let the temperature vary by as much as factors of 2, around a couple of million degrees. Let this region be around the star be sufficiently opaque that occasionally it actually starts to become convective. In other words, bubble. And you tell me that this is going to be steady. You see, steady is something that we have only in the longest term. When we talk about stationary accretion flows, this is an idealization. Now, what happens in the bathtub is incompressible, it's highly viscous, it's low temperature, it's a single phase. When you have an accretion disk, very small changes in the column density of the material can change the opacity of that material. If it becomes more opaque, it can't radiate as well. So it puffs up. When it puffs up, it can now radiate, and so it recollapses. That doesn't necessarily become an oscillator. In dwarf novae, it can. So the outbursts that you see in, say, SS Cygni are accretion flows that have a kind of clock because of this instability. But that doesn't have to be a clock. It can be noisy, and that's what I think one has here. You certainly see that in other disks in non-novae, like beta, like everybody's favorite beta Lyra, the prototypical messy eater binary, you know, an algol system that has a thick disk around a normal star. And that varies all over the place. One eclipse to another, and the disk doesn't have the same structure. An old favorite of mine, BM Orionis, which is a pre-main sequence system in Orion, in the belt. Actually, it's in the trapezium. Has a week-long period over months and years. Its accretion disk changes structure. It's never quite the same. So in those cases, we're looking at accretion around ordinary stars, so we're not getting X-ray fluctuations and all of the attendant environmental effects that that would produce. But you're still getting fluctuations all over the place. Only
We have a
I say
question
this as
from
a
the.
theorist, okay? I think I can confess, only theorists believe that there are things like steady state disks in the world, or that there are spherical stars, or you can go on and on and on. We learn this because otherwise we can't solve the problems. But the thing
Round
that's
goals.
interesting is that once you have, and now I'm being very serious, once you have the expectation of what steady means and what steady should look like, you can focus on the things that are not. And that way you learn something. Noise is a good thing. It's not predictable, but it reveals, but it's not something that just happens. It is connected with deep processes, okay? So if you have something that's changing its structure, and maybe this is also related to the rate of mass transfer, then we can learn something by looking at that relationship. Okay? I hope that.
Yes, okay. What I understand is that there is less information in regularity.
Yes, one of the remarkable things about things in steady state is they don't know about time. When you have a perfect clock and
Steve,
you don't put
please.
the numbers on the face, then you can't tell which cycle you're in, right? You have to break the symmetry somehow, otherwise you can't learn.
Yes.
Okay. Steve, please. We have a question from the chat. Do this type of symbiotic novae seem likely to generate neutrinos to give us a heat up, or are the energies involved not sufficient to generate them with enough flux for current detectors to see them?
Let me make sure I understand the question. Is this for the quiescent state?
I don't know. This is a question raised by Neil. Perhaps he can
François,
take the micro.
I can clarify. I'm thinking there's obviously interest these days in keeping an eye out for neutrinos coming from supernovae.
I'm sorry,
question is,
neutrinos.
do this type of novae generate neutrinos in measurable quantity?
There's a bit of controversy about this. I'm going to go with a fairly strong statement. You will be able to generate, under the most extreme conditions, you might be able to generate neutrinos in some way. They won't be detectable. You will see very high energy gamma. We've already done that. I mean, we already have seen that. But whether this is going to produce anything that's analogous to what's claimed for blazars, I don't think so, because you don't have those, you don't get those energies, not in any detectable form.
Thank you.
I have enough trouble seeing above a couple of GeV in gammas. So getting into the region of where you would have a substantial enough acceleration, no, I don't think so.
Okay.
Okay, another question I received by a guy attending to the session. He has had information from a professional astronomer that a planet could orbit in the system.
Sure, why not? Yeah, I mean, okay. In order for a planet to have survived, it would either have to be very far out, or it would have to be around the red giant. It couldn't possibly be around the white dwarf unless it had been captured within some other orbit. But sure, we know lots of triple systems, and you can have you can perfectly well have a planet orbiting a red giant. There's nothing unusual about that. And there are white dwarfs that have planets around them. There are neutron stars that have planets that are somehow formed differently. But if you're forming a white dwarf and it's in this kind of system, remember what I said, the white dwarf has to lose its envelope. So that means that that it goes through normal stellar evolution. So if you have a planet that's closer than a couple of AU, which in this case would mean about the distance to the red giant, it's very unlikely that that planet wouldn't be completely absorbed in a common envelope or evaporated or both. So yes, there may be some other rocks around there, but nothing to write home about. Certainly not anything that affects the orbit. And in fact, the new orbit by Feckel, Hinkel, Mikolayevska, the one that's just appeared, that David Boyd had signaled in the spectroscopic group that's appeared in archive, the new determination of the orbit, I think, leaves very little room for anything more massive than about Venus or the Earth, which makes it completely uninteresting.
Thank you.
No, the
Okay.
modulations that you're seeing are now the modulation in the disk structure could very easily be from not it's a circular orbit. That's clear. But it could be that you're seeing changes in the wind accretion rate and that this is driving fluctuations in the outer part of the disk. I haven't seen anybody bother thinking about what this means. But if you've got small changes in the terminal velocity of the wind, this flips the direction of the flow slightly. And so at the boundary of the disk, this is effectively a radial forcing, which can generate anything within the disk that you want. It's essentially creating a supersonic piston that's oscillating on the background of the flow. And that can create spiral shocks and produce a characteristic emission profile in the photometry. I wouldn't be surprised if something like that is going on. That doesn't indicate anything about the beginning of the explosion. It may very well mean that it changes the structure of the disk and that this happens in the cycle at the point where the wind has relaxed. So it's long enough after the explosion that you're seeing something like this. I don't know that, but that's one of the things that can produce those changes.
Okay, other questions, guys and girls? No?
Because time for drinking.
One more time, thank you very much, Steve. The only
I'll send you
problem,
I'll send you the figures so they can be made
yes,
available.
thank you very much. The only problem after 2 hours is that I think that we have much more questions to raise to you.
I'm always on email, and we'll be getting together in a couple of weeks, right?
It's fantastic. Really, thank you very much.
I have to thank all of you.
Yeah, but
You
I
really
think
are
that
angels.
we shall have to study the system, and it will take much more time for us. No, no, it's fantastic.
So
Yes, and please, Steve, if you could recommend us a kind of textbook to complement your speech. You see, something to study quietly. To
um,
it would be much appreciated.
it might before the 20 or at the 2021 outburst for RSO, with Francois, I had put together notes for ARAS about what happens during that event. That might be useful for all of you. So Francois, if you've got a copy of that, I think you had done that as a special number of the Eruptive Variables newsletter.
Yeah,
So that might be one that could be useful for people. Otherwise, I'm afraid the conference from the 2006 outburst is hopelessly out of date. There's the paper that Alessandra Azzolini is first author on, that was the result of her thesis, that's in Astronomy and Astrophysics from a couple of years ago, that would, I think, put much of this in perspective. It's much more on the technical side than the RSO paper, but perhaps the two of those together would be useful. So I can, Francois, I'll send you the reference for that one, but if you could perhaps put up the other one, that could be useful. I'm afraid, well, there's also the one that I just did for the Elsevier, for the encyclopedia, that at least has the perspective on classical novae. So I'll put that up for you too, okay? I think you have I think almost the final version.
Thank you, Steve.
Well, thank you for. Yes, I'll make sure that it's supplied.
thank you very much, Steve, again. So next section in 1 month.
Is it a month or 2 weeks? When are we doing this?
As you wish. 1 month could be correct.
Yeah, let's make it a month.
Oh, yeah.
Okay.
And we shall have an agenda until June.
Okay.
That's
Next
very
one will be,
okay,
I
I
think,
think,
on
yeah.
mergers and,
Huh? And after holidays,
okay,
and perhaps second year for the sessions.
if people can
Yes.
attend it.
Very interesting, I think, for everybody. Thank you so much, my dear Steve. Oh, dear Steve.
Yes.
Okay,
Thank you very much, Steve and François.
good night.
Yes.
Thank you,
That's great.
Steve. Bye, Steve.
Thank you very much. Bye.
Bye-bye.